In recent lectures, we described how to compute vector quantities using the cross product. Today we'll discuss how to compute cross products in cases where we have vectors represented by components in a Cartesian coordinate system. Let's consider a specific example where we are computing the torque. Imagine that we have some object, represented by the red dot here, whose location is represented by the position vector r in the particular coordinate system shown. Let's also imagine that a force F is applied on the object as shown. Choosing an axis that passes through the origin, let's find the torque on the object due to F. As we know, the torque is the cross product of r with F. In this case, we also know both vectors r and F in component form. Now, before we insert the specific numerical values, let's write both r and F in a more general way in component form. We'll state the result for each component of the cross product, in this case each torque component in turn. The x component of the torque is y times F sub z minus z times F sub y. Now, if we have the expression of one component in hand, like we have here for the x component of the torque, we can find the others by permuting the letters x, y, and z. That means to get another torque component, just replace all the x's by y's, all the y's by z's, and all the z's by x's. So, for example, to find the y component of the torque, we see that we replace t sub x with t sub y. And on the right-hand side, y is replaced by z, f sub z is replaced by f sub x, z is replaced by x, and f sub y is replaced by f sub z. To get the z component of the torque, starting from the y component, we see that we do the same thing. So, in this case, t sub y goes to t sub z, z goes to x, and so forth. We can now go ahead and plug in the specific numerical values for this example, first starting with the x component of the torque. Then we do the same thing for the y component. And now finally for the z component. And we end up with this final result. Now there's another way to visualize and to remember the same calculation by using a determinant mnemonic. If you have had prior experience in computing determinants, then you may find this method will help you remember how to calculate cross products from vectors in component form. Again, let's start with the vectors r and f expressed in general component form. Then we will form a 3x3 matrix as follows. In the first row, we put the Cartesian unit vectors as shown. In the second row of the matrix, we put the components of the first vector in the cross product. Here, the first vector is the position vector r, so we insert the components of r as shown. And finally, in the third row, we now put the components of the second vector in the cross product, the components of the force F in this case. Now let's compute each torque component, starting with the x component. Here, we're using the procedures of finding the determinant of a 3x3 matrix by writing it as the sum of terms involving the determinants of 2x2 matrices. We identify the correct 2x2 matrix for the x component by crossing out the row and column that intersect with I hat, the unit vector for x, as shown. The remaining uncrossed terms for the 2x2 matrix are now shown. Now, to compute the x component of the torque, we compute the determinant of this matrix, which is y times f sub z minus z times f sub y. We multiply this term by the unit vector I to remind us that this is the x component of the cross product, the x component of the torque. We follow a similar procedure for the y component of the torque. Cross out the row and column that intersect with j hat, the unit vector for y. Then take the determinant of the remaining 2 by 2 matrix, which is x times f sub z minus z times f sub x. Note here that we multiply this result by minus j hat. The change in sign is part of the standard procedure for reducing a 3 by 3 determinant to a sum of terms with 2 by 2 determinants. So let's make sure we don't forget that sign. Finally, we do the z component of the torque. Cross out the row and column that intersect with k hat, the unit vector for z, as shown. Then take the determinant of the remaining 2 by 2 matrix, which is x times f sub y minus y times f sub x. And again, in this case, we multiply the component by plus k hat to obtain the final general result. Now we can insert the specific numerical values for our example, and we see we obtain the same result for the torque that we found earlier. Two final notes. The order of the cross product matters. If the order of the vectors is reversed, then the sign changes. So, for example, F cross R shown here is equal to minus the torque. In other words, the sign changes for each of our torque components. This sign change comes out automatically from our determinant method, since changing the order of the cross product changes the row locations for the vectors in the 3 by 3 matrix. And finally, we note that while we discuss in detail how to compute torque from vectors in component form, these methods will work just as well for other vector cross products, such as the vector angular momentum. We'll have a chance to practice this for both torque and angular momentum in some upcoming problems in our class homework.